Hi everyone, my name is Nishan Kishore. In this section, we'll be working on linear regression. First, a few housekeeping notes. We assume that you have some previous knowledge of correlation, of linear regression, and of logistic regression. This section is purely a lab that works through the mechanisms of how we calculate some of our important estimators for these processes. However, we don't go into very deep depths of how we interpret these or how we should appropriately run a study or do modeling or any of those things. So we do assume some coursework, some bookwork, something like that as a basis. We assume that you have some background in R, as we won't be going over how to set up RStudio, what libraries, how to install libraries, or any of the maintenance required to run something like RStudio. The purpose of this lab is to dig into the mechanism of these concepts and calculate them by hand in R, so that you have a deeper understanding of how these equations actually work and perhaps even intuit what they mean. We will review some basic R data cleaning steps as well, but the focus again is going to be on the calculation of these equations of interest. These sets of labs are produced in order and may refer to previous sections. Linear regression. In this section, we will calculate estimators in a simple linear regression. By simple linear regression, I mean one predictor, one outcome. We will identify connections between the estimators and correlation, and we'll produce figures to evaluate the regression. So let's go ahead and try it out in R. All of our labs are run through an R Markdown format. This allows us to work in little chunks of code and view our results in line. To begin, we're going to simply load the package tidyverse, which is a package of packages that gives us things like dplyr, migrator, other packages or libraries that might be useful for us to work in R. For this section, we'll be using data from the Framingham Heart Study. While these data are available for this course, you can use any data set with two continuous variables. Here we'll read in our data with the read CSV function, and we will select only the BMI and the systolic blood pressure measurements and rename them to lowercase bmi and lowercase bp underscore over. You'll see as I run this chunk, our data set shows up in our environment. We have 11,627 observations and only our two variables of interest as we saw before. Let's take a moment to visualize our data. We'll use R's inbuilt ggplot function to do a simple graph or figure which shows BMI on the x-axis and systolic blood pressure on the y-axis and a scatter plot of the two variables. Let's assume that we've been instructed that a BP over 50 or a systolic blood pressure over 250 are incorrect. The researcher says that they were just errors in measurement or something of that nature. We'll take these out of our data set along with any NA or missing values. These are arbitrary decisions that I'm making right now, simply to make our analysis a little bit easier and to demonstrate how you might subset your data in important ways or drop missing variables. For any study that you conduct, you will want to consult with the researcher, the principal investigator, to determine what sort of cleaning steps you would take or that might be necessary for the work that you do. Here, we filter out the BMI, so we're filtering our data set so that it's only for BMI below or equal to 50 and blood pressure or systolic blood pressure that's below or equal to 250. And we'll drop all of the missing variables. Again, we'll show our plot. And as you can see, our upper limit on the y-axis, or systolic blood pressure, is now 250. Our upper limit on the x-axis, or BMI, is now 50. We're going to take these data and run and select a random sample from them. The reason that we're subsetting data to only 20 observations is so that you can see step by step exactly what happens as you run the calculations necessary to figure out our estimators or to do the linear regression. In this case, I'm going to use this function set seed at the beginning to 1, 2, 3, 4. And this ensures that when I take a random sample out of this data set, I take the same sample every time. This just helps us make sure that we have something that's reproducible. If I collect the same sample now and get a specific measurement of an estimator that I'm interested in, it's the same thing I'll get next time. If I were to comment this out, I would just get a different result for our sample every time, which is also fine. As you can see, we have a new data set we've created called DAT2, which contains 20 observations of 2 variables. And here's a small subset of our data set of interest that we've just created. Let's plot our new data set. As you can see, these are far fewer points, only 20 of them instead of the 11,000 something. And importantly, we're still subset within a specific space, and we can see clearly what's happening in terms of how these points are linked to each other. There's a lot more white space for us to work with. So starting off, everything in R is either an object or function. There are many functions which we can use to perform a regression, including calculating it by hand ourselves. And there's even a function for a linear regression in ggplot, which will allow us to automatically place a linear regression line on our plot. Here you can see that I'm doing exactly what I did before. I'm doing ggplot, describing my BMI as X, my systolic blood pressure as Y, introducing the points that I want for the scatter plot, creating a base theme for the background, setting the label so that the X says BMI and the Y says systolic blood pressure. And the only other thing I've added is this geom_smooth function, which adds our linear regression line, which is specified here with the method equals LM, or linear model. And I've set SE, or standard errors here, to false so that we don't show the error bars around our regression line. As we run this, you'll see that this, according to the inbuilt R function, is the line of best fit, or in this simple linear regression, of these 2 variables of BMI versus systolic blood pressure. Our job now is to reproduce this manually. So let's take a few moments to remember the key formulas of doing a simple linear regression. Here are 5 that help set the basis of the notation that we will be using. First, we have the expected value of y, or our outcome, is equivalent to beta 0 plus beta 1x. First, we have that our expected value of y is equivalent to our coefficients of interest beta 0 plus beta 1 times x. Here we're simply saying or describing the model that we're using. It's a simple linear model which includes an intercept term, our beta 0, and beta 1, which is our term for slope here. Our second equation is y sub I is equal to the estimate of beta 0 plus the estimate of beta 1 x sub I plus epsilon sub I. The key difference between the second equation and the first one is that we first have the estimate, or the hat, over our coefficients of interest, beta 0 and beta 1. Here we can see that we're not using the population parameter of some unknown beta 0 or beta value, but rather the estimators that we have ourselves. In the first equation, we're simply describing the model, which says that there's some population parameter for beta 0, there's some population parameter for beta 1, and we're multiplying this by the value for x to get our average value for the outcome. In the second equation, we're describing each and every individual in our observation. So let's replace I for the second equation by 1. We're saying that for that individual, the outcome, or systolic blood pressure, y sub 1, is equivalent to our estimate for beta 0, whatever that ends up being, plus our estimate for beta 1 times x sub I, or x sub 1, which is their BMI at a given point, plus some epsilon sub 1, or error term. Essentially saying that it's not necessarily going to be a perfect match, but for this specific individual, there is some error or some residual which links the predicted value to the actual outcome of interest. Our third equation shows the estimated value for y sub I is equivalent to y sub I minus the epsilon sub I. So once again, let's think about this in terms of the first observation in our model and replace i's with 1s. Here, we're saying that there is some observed value for y, again, systolic blood pressure, for an individual. So let's take a moment and actually look at that. Our first individual in our data set has a systolic blood pressure of 146. However, our estimate or predicted value for that individual, which is the y sub I hat, doesn't necessarily include or won't necessarily result in being exactly 146. So we have our observed value, which is y sub I, our estimated value, which is y sub I hat, and our epsilon value, which is the error term. And this is simply saying that there's going to be some error term that is the difference between our observed value for y and our predicted value for y. Number 4, we have our estimator for the outcome, y sub I again, is equivalent to our estimator for beta 0 plus our estimator for beta 1 times x sub I. The only difference between the equation in number 4 and the equation in number 3 is that rather than looking at the observed outcome, or y sub I, we are now looking at the predicted outcome, or y sub I hat. What this means is that we're no longer looking at the error term and are simply linking the right side of our equation, our beta coefficients and our predictor value, to the left side of our equation, which is our predicted outcome. You'll notice, for example, that y sub I has a hat over it, whereas x sub I does not, because this is our observed value for x sub I. Finally, we have equation number 5, which shows that epsilon is distributed normally with an average value of 0 and a standard deviation of some sigma. All this really goes to show, and perhaps one of the key important things about linear regression in general, is that the error terms, the residuals, have an average value of 0. So across all our samples, while an individual might deviate from the prediction by fairly large amounts, the average value of that error, the average value of epsilon across our data sets should be very, very, very close to 0 if these estimators work. Take a moment to look at these, and again, make sure that you have a deep understanding of them and can explain them in layman's terms. Make sure you understand the difference between a variable or a coefficient with a hat over it, which is an estimator, versus one that's an observed value or a population parameter. And finally, ensure that you spend some time really, really looking into the error term, epsilon sub I, and understanding how it's created and how it fits into this larger equation for the linear regression. Secondly, we have our terms that are actually used to calculate our beta coefficients. First, we have our estimator for beta 0. Remember, if we were looking at the actual population, some hypothetical population parameter for beta 0, or this intercept, that would be an observed value across the entire population. In this case, we only have a sample, and so we're going to estimate beta 0. In this case, the estimate for beta 0 is given by y bar, or the average value for y, minus the estimator for beta 1 times x bar, or the average value for x. You'll notice that one of the key things that we need to actually calculate beta 0 is our estimator for beta 1, or beta 1 hat. So we go on to the next step. In the next step, we have our estimator for beta 1 hat, or the estimated beta 1. This is described in two pieces. First, in the numerator, we have our our individual values for x sub I minus x bar, or the average value of x, times our individual values for y sub I minus y bar, and then summed all up. In the denominator, we have simply x sub I minus x bar squared, and then summed. I would like you to take a moment and think about how the numerator for the estimator for beta 1 compares to the numerator for the estimator for the correlation coefficient, or Pearson's correlation coefficient. Now that we have these, let's go ahead and do them step by step, or by hand in R. First, we're going to convert our value for BMI into x and our value for BP over into y using our mutate sections. And then we'll calculate our x bar, which is just our mean or average x, and y bar, which is our mean or average y. If you look at the data, you can see now that we both have x, which is equivalent to BMI, y, which is equivalent to BP over, and x bar and y bar. As you notice, x bar and y bar are not values that change. These are static values that describe the average x or the average y for the data set, whereas x and y change for each observation. So let's take a moment for our estimator for beta 1 to look at the different pieces that we need. First, we have xi minus x bar, the section in the equation in the numerator, and we have yi minus y bar, which is also in the numerator. Importantly, in the denominator, we solely have xi minus x bar. So we can calculate all of our steps in one go. First, we have xi minus x bar is equal to x minus x bar. Y minus y bar is equal to y minus y bar. And our numerator, again, is simply given by, this is again before we sum it, but our numerator is given by xi minus x bar times yi minus y bar, and our denominator is simply xi minus x bar squared, or times itself. You can see that we haven't finished our summation steps yet. So for each of these values, for xi minus x bar, for minus y bar, and for the numerator and denominator, these vary by each observation. In our final step for beta hat, we simply sum the entire numerator and divide it by the sum of the entire denominator, resulting in an estimate for beta 1 hat, which is 2.068. I'm going to take a pause here so that you can evaluate what you've learned in your course, look at this estimate for beta 1, which is 2.06, and interpret it. Now that you've conducted your interpretation for beta 1, let's take a moment to calculate beta 0 hat. As we've seen in an equation before, beta 0 hat requires our estimate of beta 1 or beta 1 hat to work. And it also requires the average y and the average x or y bar and x bar. In this case, since we've already calculated y bar and x bar in our data sets, I'm simply extracting these to the unique value. There's only one value for the average, as we've seen before, and placing this in our equation where we have y bar minus the estimator beta 1 hat times x bar. And results in an evaluation for beta 0 hat, which is, or an estimate of beta 0 hat, which is 85.086. Let's go ahead and pause for a second and see if you can interpret the estimate for beta 0. Great. So now in our data set, in our working environment, you can see that we have DAT, which is our original data set, DAT2, which is our analytic data set that we've created, and importantly, our estimates for beta 0 hat and beta 1 hat. We can put these directly into the ggplot function before and see what our line looks like. So here, for example, I'm doing the same scatter plot in ggplot as I'd done before. But instead of doing geom smooth, which we'd used before to actually use the R function to put the regression in, I'm using geom abline, which allows me to put a straight line however I want through the figure. Here, I can specify what the intercept is going to be and what the slope is going to be, color, and a line type, and quickly and easily see what this line looks like. I can also, using our previous function, put in the line from R's method. So again, I've simply just used geom smooth method equals LM for the linear model, no standard errors. And you'll notice that the line, the blue line that R produces from its own internal linear regression, is exactly equivalent to the line that we've just generated using our estimators. You can also scroll up and check to see how this compares to the line we plotted automatically. While we've calculated these estimators for the simple linear regression by hand, we can also check them using R's built-in functions. So here we're going to use the LM function, one of the basic linear regressions in R, to check out the estimates against the one that we calculated. So here I simply run LM. I describe our formula. So Y here is our outcome linked to the right-hand side of X, which is our BMI. So Y here is our systolic blood pressure, X is our BMI, and I specify the data that I'm interested in. As I run this, I get an estimator for the intercept, which is a beta 0 hat of 85.086, and the estimator for X, which is beta 1 hat, becomes 2.069, exactly what we'd calculated earlier. Again, take a moment to look through these and make sure that they compare with the estimates of the betas that you had before. An important step in evaluating how a model works is to think about the residuals. If you go back to the equations that we looked at before, in this case, those error terms or residuals that we're talking about are the epsilon sub I. And we are, of course, interested in looking at that. If our model is all over the place, it might be something we might be concerned about. The specific steps for evaluating residuals, for evaluating the model, will be covered in course. And again, this is just the lab where we go over the actual mechanisms of how we might look at this. So first, we calculate our estimated value of the outcome, or systolic blood pressure, or Y sub hat. Here, we can see that this is simply, again, based off the equations above, beta 0 hat plus beta 1 hat, or the estimated value for beta 0, the estimated value for beta 1, times our values for X. And our error terms become our observed value for Y minus our predicted values for Y, or Y hat. So this is, again, simply the difference between where our model says Y should be by this line of best fit and what we actually observe in reality or in our data. Let's take a moment to run this. So now we have a data set. So if you simply look at that too, this will include a term called error. Based on the equations above that we've reviewed, specifically equation number 5, what would you expect the average value of the error to be? Take a moment. You have your prediction? All right, let's try it out. So now we're simply doing summary of dat2 $error. And you can see, as we said before, that error, especially the way that we do this equation and that we use these estimators, that we have an assumption about the distribution of the error, and that holds firm. In this specific case, even though we have errors that go all over the place, you can open up dat2, you can scroll all the way to the right, and you can look at the error terms. There are some where the error is 55 off. There are some where the errors can be fairly large. However, the average value of the error across the entire set is going to be 0, based off of the requirements and the assumptions of the estimators that we've used. Finally, we can use this information to actually plot out what the error looks like. So as I run through this, I can create a plot where I have error on the y-axis, the observations in my data set on the x-axis, and this horizontal line at 0 shows me where the error should be. And as you can see, the error fluctuates above and below this line. Again, you would want to consult your coursework to learn how to best evaluate these residuals, and we will simply plot them and confirm certain assumptions about our modeling steps. Let's do the exact same thing we've just done, except now using R's built-in functions. We do want to double check that what we're doing by hand is exactly what comes out when we use R's built-in functions. So first, we will calculate all of our residuals. So the residuals here are simply ones where we have our model and we extract them using the residuals function. So this data set that I have called resid is simply an array of different variables. And some of these might look very familiar to you from what we evaluated from our hand-calculated errors before. Importantly, we can do the exact same graph that we did previously and see that our results for the figure are identical. Our outputs, our calculations for residuals, are exactly the same whether we did them by hand or we did it in R, as we expected, since they should be using the same background equations. Finally, as you might know from your coursework, there are important measures of the model, such as R squared and the adjusted R squared, which we'll use to evaluate the model. Again, we won't necessarily go into the interpretation of these right now, but we can talk a bit about how these are calculated. So let's take a moment to look at important estimators or measures of model fit. We won't go into the interpretation of these or specifically into why we calculate them in certain ways, as this will be covered in the coursework. But we'll spend a moment here to calculate them by hand and verify that what we get by hand is what we also get using R. So first we have our R squared, which is simply 1 minus the sum of squared errors over the total sum of squares. Here we look at 1 minus, in the numerator, the sum of squared errors. So we have our observed values for y sub I, and then we have our estimated values for y sub I, or y sub I hat. And we simply look at the difference between them, and then we sum it up. So we sum the squared errors of this. And then secondly, we have the sum of squares, which simply becomes yi minus the average outcome for y squared. So how far does y deviate from its average value? For our adjusted R squared, we're going to use our estimate or our value for R squared, but we're going to adjust it for the number of observations and the number of parameters we have in our model. There are many different reasons to do this, but for the purposes of this lab, we'll simply say that the adjusted R squared accounts for somebody having infinite or n number of variables in their data set and penalizes you for every extra variable that you might have. So let's go ahead and calculate these and see how they line up against our model. So first, we have our sum of squared errors. So we've already calculated our errors, so we simply square them and sum them to get our SSE. Second, we have our total sum of squares. So we have our observed value for y. We have our value for y hat. These values are then squared and then summed up again. And then our estimate or our calculation for the R squared is simply 1 minus the SSE over the TSS. So let's run this really quickly. And we can see that our value for R squared is 0.101. Again, we're not going to go into the interpretations, but that isn't very amazing. Second, we're going to incorporate our value, or we're going to incorporate how many observations we have and how many predictors we have into our estimate for the adjusted R squared. So in terms of the number of observations, we have the n row of dat2, which is 20. And then in the number of predictors, we simply have 1, which is x. So then our adjusted R squared here becomes our variables of interest that we've seen before. And we result with an adjusted R square of 0.05, which, believe it or not, is even worse than 0.1. So let's take a moment to actually look at the model outputs using the LM and then the summary function, which will output the values that R calculates. And again, just as a recap, we can see that our estimator for the beta naught is equivalent to our estimator for the beta naught hat here. Our estimator for beta 1 is equivalent to our estimator that we calculated by hand here. And below, you'll see our estimators for the R squared, 0.101, and the adjusted R squared, 0.05, both of which we have calculated here. Again, as a challenge step, take a moment to go back and try to code by hand everything that we've done, but for the entire data set. do the plots, calculate our estimators of interest by hand, compare them against the model outputs, and see if you can gain a bit more intuition about how these estimators work, how they link together, and how they relate to the other concepts that we've learned so far in this course. Thank you.